All right, good morning, everyone. My name is Sam Miller. I'm excited to be at my first GR-Con presenting my progress in an open source implementation of Halo, which is otherwise known as 802.11ah. It's a substandard of the Wi-Fi spec. If we could all hold questions to the end, I know we're getting close to lunch, but I'll do my best to save some time for any questions you might have. All right, so at home I like to play with SDRs a lot, obviously, like many of us here. And I like playing with Mesh-tastic devices, other IoT nodes like Zigbee, Bluetooth, and others. And one day I stumbled on Halo devices, and I thought it was pretty cool because it offered a good trade-off of data rate and distance. For those of you that have used Mesh-tastic, it's a great long-range text messaging, mesh-based communication, but there's some capability to be desired if you want to send images or maybe even have like more of a traditional like IP-based mesh network scheme for something like maybe cameras or higher throughput sensor nodes. So I thought I'd give Halo a shot. And when I bought my nodes, they advertised WPA3 encryption and everything, and I was like, well, if this is an open part of Wi-Fi, let's take a look at it with an SDR and see how much I can learn from it. But unfortunately, kind of like I have stated here, like what's the main problem? There weren't a lot of devices available. There weren't a lot of open source repositories to be able to already decode Wi-Fi Halo. So for a protocol that was supposed to have over 8,000 devices that are able to connect in the network at one time, or be an IoT standard that has ubiquitous access, there just wasn't that ubiquity just yet. So the then straightforward but ambitious solution was to try and create as much as I could towards a full transceiver architecture in GNU Radio. And this is just so anyone with an SDR that might not want to invest in the commercial Halo devices that are out in the market today could just pick up their radio and start giving the Halo network a scan to understand and interact with it a little bit more. It also provides a good third-party debugging device if you have a Halo network working and you just want to kind of step aside with just a software-defined radio and analyze your network. So just trying to open up the use towards everyone. And one key benefit of Halo versus the legacy Wi-Fi, so I consider that 802.11n and before, is that its bandwidths are well within the range of even the most inexpensive SDRs. So you're looking at 1, 2, 4, 8, and 16 megahertz. So even something like the RTL SDR can pick up the smallest channel bandwidths available. Furthermore, some of the data rates are well achievable with commercial processors. As few as 150 kilobits per second over those 1 megahertz channels, but as you get up into the higher channels and the MIMO processing, you can get up into like 80 megabits per second, which is pretty substantial. And then lastly, kind of just like I said before, sits in that middle of that data rate and distance trade-off. So it's pretty useful for some applications where you might have like distributed sensing, like on drones, or if you're there's one application out right now actually that's pictured on the screen for the Amateur Radio Emergency Data Network. That company is Teledactics, and they set previously in July the current Halo distance record from what I could find at 66 miles with a 30 dBm transmitter and a directional antenna. So pretty impressive achievement on their part. Okay, so then what's my approach going to be in taking this ambitious leap towards an open transceiver architecture? It was a threefold step. First and foremost, I kind of wanted to have something available for people to run at the conference if they were interested. And so how that manifested itself was in the Halo activity scanner, which I'll go into detail shortly. I did try and take a step towards the full receiver implementation. I have some elements of that working, but as a whole, it isn't working yet. And we'll also cover my shortcomings on the full receive implementation. And then once I was able to do that, my ideas were to go full transmit, so we could just have bidirectional transmit and receive functionality. And I also want to take this time to thank Bastian Blossel for his contributions to GR-IEEE 802.11. I use his repository as a huge leaping point and foundation for 802.11 AH. And while my repository and his aren't compatible right now because I made some breaking changes to 802.11 in my fork for AH, eventually I would like to get it merged into GR-IEEE 802.11 so you can start to use A, G, P, AH, whichever sub-protocol you're interested in, but that does lie down the road. Okay, so first, like I mentioned, I'm going to detail my activity scanner a little bit more. This is just an overview of the GNU Radio flow graph as a whole. I'll break down every component in here and then culminate in a video demonstration. And right now you can access the code up on GitHub, so if you want to give it a shot. So the first obvious modification I had to make was to the channel lists. So 802.11 AH works in the 900 megahertz ISM band in the US, and it uses fewer channels across 5 different possible channel bandwidths pictured there on the screen. And in the experimentation that I was doing with some actual Halo devices, I found that annoyingly some of the manufacturers didn't stick to the IEEE specification when it came to the channel numbers. So I just implemented a JSON configuration file where, based off of whichever channel format that you're used to seeing, you could pair that with the frequency and the bandwidth of the channel that you're expecting, feed that into the scanner, and it would parse that configuration file in order to tell the radio which channels to look at for Halo activity. This is a fairly straightforward change, but necessary one. The next major change I had to make for AH was in the timing. So in legacy Wi-Fi, it was pretty convenient because a lot of the ratios were constant. So the number of subcarriers stayed the same across the different bandwidths, but also the ratio of the channel bandwidth to the OFDM symbol time was constant. So you always had 80 samples per symbol no matter which channel you used in the old Wi-Fi. And that made it easy in the implementation of GR-IEEE 802.11. You can just either pound define, samples per symbol as 80 or just hard code that 80 value in there. But the switch over to Halo was a variable relationship in all those factors above. So you start to see the number of subcarriers increase for each of the respective channel bandwidths. You also see that the symbol time is constant across all channel bandwidths, which means as you increase the bandwidth, you get fewer and fewer samples per symbol. So the key approach that you'll have to take there in implementing IEEE 802.11h is doing more or less an object-oriented definition for each bandwidth, so that when you're going into your receiver, you can reference the variable within that object to determine what your samples per symbol will be, and also the number of subcarriers you'll have. But for my scanner, I just focused on the 1 megahertz channel for now, kind of set the stage for that object-oriented approach, but I really wanted to get the full thing working with 1 megahertz, so I didn't see much value in trying to get all the channels working if I wasn't sure if the whole implementation was going to work right away. So this is the result of that fix. You see before on the left side of the screen where I hadn't applied those timing corrections. The flow graph was trying to tag the beginning of a Halo packet, but the tags were just kind of appearing erratically throughout the packet. But after applying the timing fix in the middle, the tags were showing up reliably at the start of each packet. So now I could reliably determine whether there was a Halo packet on the channel you're interested in, and when the start of the packet was, as well as the rough frequency offset of that frame. However, I did see that on adjacent channels, whether this was just due to poor channel rejection of the device I was using or just good autocorrelation properties on that that side channel, I was seeing some like false alarm detections. I was, on channel 1, but truly there was some Halo activity on channel 2 and I was getting some false alarms. So this in and of itself wasn't enough to be able to build a robust scanner. So I had to then add in 2 additional blocks here. So these are just embedded Python blocks. The one on the left is the main scan controller. So this is pretty standard. It takes the bandwidth available to you for the SDR that you have plugged in, and it will parse in that JSON configuration file that I mentioned earlier in the presentation and determine fixed windows that it can place your center frequency and your bandwidth so that you can see the maximum number of Halo channels simultaneously. Then it uses a frequency translating FIR filter to sweep through each of those channels with a given loiter time that you have for that channel. We'll get into this in the video demo, but I did notice that longer loiter times had like better chance of reliable detections, but obviously at the trade-off that you're lingering on channels for a little bit longer. And then the activity detector was really the way to try and solve the issue where tags might show up for adjacent channels. And just from some of my observations, I saw that generally a lower frequency offset correlated with the fact that you're actually seeing a packet on your channel. I noticed that if I was getting false alarms, my frequency offset would be higher. It would try and correct for that some more. So I used that as one threshold. And I also used the power average as a threshold. So on a certain, on the actual Halo channel, you typically saw, higher power than you would on adjacent channels. And what you see pictured at the bottom there is a successful test where the Halo scanner was moving through the different channels. And then on the channel where my devices were already pre-programmed, it was receiving packets. And for the time being, I was just outputting to the GNU Radio serial console there, so I was just getting a detection alert every time I detected a packet. So that was good news. And at this point, I was able to go do a test outdoors to see, just really how well this would work. And we're going to try and pull up a video here just to show that test. All right, so first obviously started off in setting up my Halo network, and then I was scanning everything with an SDR, just have a little mock-up of the network there, but the first thing I had to do was kind of go in and verify my network settings. So this is just doing a little bit of a sanity check, making sure my laptop's getting an IP address from each of the Halo routers that I have. Then I'm going to actually serial into each of the devices in order to verify some of the device settings, make sure that they're the same version. These devices do run OpenWRT, which is convenient. And then actually modifying a setting in the radio to turn rate control off and also fix a given modulation coding scheme. So I'm pretty much telling it to transmit BPSK, which in this case is modulation coding scheme index 0. And I'm just verifying the settings there on the screen. And I have to do the same thing for the other device, but before I do that, I'll navigate to the web console, because on there it'll actually show if there are other devices that are actively connected, as well as verify the channel frequency, bandwidth, and power settings. So that'll pull up on a nice convenient little dashboard here, and I can see that there's one MAC address of a connected device, and all the other settings matched from the command line interface app that I saw before. So everything looks good on device 1. Now I'm going to go repeat the process on device 2, just another sanity check to make sure everything's constant, and that I can actually establish that Halo network. I am doing a little bit more here than you would need if you were actually trying to run this device network. I'm just trying to be verbose about making sure my test conditions are the same. So again, setting the modulation coding scheme to 0 so these devices can communicate. And then the final sanity check is going to the configuration dashboard of the second device and ensuring the settings are the same and that it sees the first device that I went through before. And great, second sanity check passes. So the Halo devices are now communicating with each other over just a simple iPerf test, and I can now scan the Halo network. So you see the flow graph pulled up here. Is time tag-based detection on the time plot, and in the bottom you can see the Halo activity. So I got a success there when I was actually scanning past the channel. And then here I'm going to repeat the process for just a faster loader time to show that it actually skips over the desired channel a couple times before getting a final good detection on like the last sweep. So just illustrating a little bit of the trade-off that I saw between the longer and shorter loader times. And then here was the actual like distance testing I conducted, just roughly yes or no, did I receive Halo packets or not? So at my really short 18-meter distance, I got detections 50 meters away through some trees, was still able to get some packets. Even 100 meters away, I was getting reliable Halo detections, which was awesome. But about 200 meters away was when my signal was just not making it back to my receiver, my software-defined radio anymore. So that's just to illustrate a little bit of what like the Halo network's capable of. And now we'll kind of go through where I fell short in implementing the receive implementation, and maybe get some ideas for how I could do better in the future. Okay, so the full receiver doesn't really add much on the end. It's now just trying to take the OFDM signal, take it into the frequency domain, and actually decode some of the packets after equalizing and synchronizing. So the first modification I had to make was Halo applies a different training field sequence to the packets in order to equalize in the time domain. So just as the 802.11 spec showed, I just applied an inverse Fourier transform on the Halo packet in order to get that proper input into the equalizer. But then again, I was using BPSK, so the equalizer shouldn't have a significant effect here. I will say that this will probably have a better effect when the rate control brings higher order modulation schemes into the picture. But this I felt was still a necessary step. The next step was modifying the physical layer protocol data unit format, or PPDU format. The signal field of Halo is actually way more verbose than that of legacy Wi-Fi. So I was actually using this as my litmus test to determine whether my receive was actually working or not. Because as I showed in the video, I was setting the exact modulation coding scheme. So I was expecting to see that exact same modulation coding scheme in one of these signal fields. And then there's also a length field in here. So that would have provided an additional sanity check in saying, well, did my length field match about roughly how long this packet I received was? So while I did get the deserializer for this written up in C++, I wasn't getting reliable receive detections, which was telling me that there was something earlier in my flow that was going wrong. So somewhere between detecting the Halo packet from the scanner and for taking it out to bits in the signal field. But I did see that if I was able to get reliable bits out into the signal field, that it would have been fairly straightforward to then take that a step further and get actual information from the data field. And I was testing this all with unencrypted data, so I should have been actually able to kind of see this in plain text flying over the air. And another point I'll mention here, kind of in a similar vein to how the Halo timing was variable and needed a object-oriented approach, the PPDU format is also variable between various Halo channels. So there's a great variety in the signal field, even between the 1 megahertz, 2 megahertz, and 4 megahertz channels. So this is also going to need a very catered approach for decoding all the different available channels on Wi-Fi Halo. So here's where I think I could really do better. I was trying to, kind of like rush to get a solution, but you know, I'm reminded that being more deliberate is the correct and most thorough approach. So I think by implementing more intermediate tests in that frame equalizer block, I could try and isolate where my problem is. So realistically, and I have it pictured up on the screen in the bottom left there, the halo equalizer is trying to do four things. So breaking those steps out and kind of being rigorous about looking at the inputs and the outputs to each block, testing each one to make sure that it matches what I would expect, and see where I'm going wrong. Like I mentioned before, I'm doing BPSK now, so equalization shouldn't have that much of an impact, but where I do believe something might be throwing me off is in the polarity of the fixed pilots and the possibility of traveling pilots. So I might just be implementing the polarity of fixed pilots on Halo wrong, and that's affecting my ability to synchronize to the actual data that's coming over the air. But also, Halo in the standard says that it can either have fixed pilots or this concept of traveling pilots, where the pilots will, the subcarrier index will actually vary with each symbol. This is to try and get a better characterization of the OFDM channel. So I'll probably have to, you know, branch my code off into different branches to try and implement fixed pilots in one, traveling pilots in another, to see which approach wins out. Unfortunately, I did try and dig into the configuration of my Halo devices, and I wasn't able to control the traveling pilots like I was able to control the modulation coding scheme. So this one I might just have to brute force a little bit more, but those are the two areas I think that might just be throwing the receive off a little bit. Yeah, here are some of the resources I used. I want to thank Mark for helping me out earlier in the week. I made about like 12 SIG-MF recordings of my Halo device. So you can scratch off the upload to IQ Engine as pending, because it's actually there right now. And you can play around with some Halo recordings if you're so inclined and want to check them out. I made recordings in the 1, 2, and 4 megahertz channels at 3 various modulation coding schemes. So I guess you can call it a race now to see who's going to decode Halo first. And just some other resources I thought were really helpful and helping me get a better grasp on the protocol, you know, and dig into it more. And I will say the specification is free and open by IEEE. Even though it's 4,000 pages, there's only one chapter on Halo, so it's a little bit more digestible than you would think. Yeah, just thank you for attending. I'll stick around for any questions you might have. And if you want to see the Halo devices, like in person, how they work. Otherwise, give me a follow on some of the socials if you want to follow along with my progress. And yeah, I'll take any questions if you have them. Thank you.